Hey everybody, happy Friday. For today, I'm going to be running through what would have been our first lab. So I would have actually done this last week Friday with you guys if we were here. And again, I was kind of playing it by ear with how to run Friday classes and with obviously the lab portion of this of AP Chemistry being such a big chunk of this class. I've been toying with how to do this. But what I'm going to do for you today is I'm going to record myself doing your very first lab that you would have done last week Friday if you were here. And then we're going to answer some questions about it. This will absolutely 100% help with your topic 2, which is going to be due on Monday now. I switched that from Thursday to Monday next week, so please be aware of that. The questions that are getting asked today that I am asking you to also turn in as a part of today's class will help with your homework topic 2. So let me explain what we're up to. I have posted the document for this lab on the plans, and it is also in the resources tab of your It's Learning page for our class. I'm going to pop out of my presentation mode and just go to full screen on the camera. And it looks like this, okay? So if you can kind of see your document that you're looking for, which I posted in more than one place, looks like this. There's a huge procedure, okay? I'm not going to read through any of that. That's what I'm going to be doing, all right? So as a part of this video, you're going to be watching me run through this lab. Okay, so let me kind of explain what we're up to. Let me give you a lay of the land, so to speak, and then I'll run through some of the procedure and get some things set up. All right, so today we are going to be mixing sodium carbonate and calcium chloride. All right, these are both just salt compounds. We'll talk a whole lot about salts later in the year. Don't worry too much about that definition just yet. But we're going to be dissolving both of these in water and then reacting them, okay? The result of this chemical reaction is going to be what's known as a precipitate. A precipitate is when you have two solutions, aqueous solutions, meaning, again, something is dissolved in water. I mix those aqueous solutions together, and then a solid forms. The solid is what's known as a precipitate. So today's lab, which again was an introductory lab, which we would have done last week, is all about a couple of concepts. We're going to learn about net ionic equations today. We're going to learn about precipitation reactions, and then we're also just generally going to learn some lab techniques, okay? And these are called gravimetric lab techniques involving gravity, all right? So that's things like massing and filtering, and both of those are a part of today's lab. So let me get some things ready, and yeah, we'll get started here in just a little bit. All right, so I've got my safety glasses on. Obviously, safety is very important. And if you were here, again, hair ties, closed-toed shoes, safety glasses, safety goggles are always a must in the lab. So first thing I'm going to do, I am walking through the procedure, by the way, right? So again, this document that I've posted, I'm walking through this procedure. You're more than welcome to kind of follow along with me, and I'm not going to show everything because it's going to be too long, but I will show you the important stuff and show you some technique things as we go. So first things first, I'm going to mass out 2 grams of sodium carbonate. This is the sodium carbonate right here. I'm going to do that in a beaker. So this little balance over here, and I'll get a little bit closer, okay? Sorry for the shaky cam. This is what's known as an analytical balance, all right? It has this cage around it with these sliding doors, okay, to guard the currents or the air in the room. This goes all the way down to the thousandth place. This is way better than any balance you used last year in regular chem. This thing is over $1,000, okay? It's an expensive piece of lab equipment, and it's specifically only for AP Chem because it's so expensive. So I'm going to be using this balance, and I'm going to be massing my sodium carbonate directly into my beaker. So I put my beaker on the balance, and then I hit the tare button, which brings it to 0, okay? That's appropriate technique, right? I don't care how much the beaker weighs. I could record that mass. I could add my chemical and then subtract the mass of the beaker, but that's just a waste of time. So instead, I'm going to put the beaker on there, tare the balance is what it's called, and that makes it to 0, and now I can add my sodium carbonate. So I'm going to use this, which is called a scopula. Okay, it's kind of like a spoon-knife hybrid. So I grab some of this sodium carbonate, and now I'm going to use a technique that I learned in college. All right, so I have my full scupula hanging over the top, and I want around 2 grams. I don't really care how much it is in terms of like whether it's less than 2 or more than 2. I just want around 2. So I'm going to tap my wrist, okay? And when I do that, the powder slowly falls off so I can control how much I'm adding. I hope you're here eventually this year and we have a chance to do this for real, because it's an important lab technique that you'll use in your college chemistry class if you take chemistry in college. So I'm getting close. I slow down, lighter taps, and I'll stop right there. And I'll put the remainder back in my container, and I'll record what I've taken. So I'm using 1.947 grams. Oh, let me close the shield. How's that sound? So sodium carbonate, I have 1.947 grams. Okay, and I just made a little spot for it on my sheet. You should record this. You're going to need this later as a part of our problems. Okay, I'm going to pause it. I'm going to mass out the calcium chloride, the other reactant that we have, and then I'll come back in just a little bit. All right, so I have now massed out the calcium chloride as well, and I have about 2 grams of each of my powders in these beakers. I would like you to also record the mass of the calcium chloride that I've added, okay? So I have 1.947 grams of sodium carbonate and 1.961 grams of calcium chloride. We're going to need those later for some problems, okay? All right, now, the next step of my procedure says I should totally dissolve these compounds in water. And I say about 20 milliliters. Here's the deal, and this question would have come up if you were here, I promise. We want to dissolve them in water. But if I use 10 milliliters, or if I use 100 milliliters, does it change the amount of chemical of the sodium carbonate or the calcium chloride? And the answer is no, it doesn't, right? The moles of sodium carbonate is based off of the mass I just added. So I can dissolve this in any amount of water that I really want to. My point in putting 20 milliliters on the procedure is to just ensure that you don't use way too much, right? So I'm going to do that. It's about 20 mils. And that's about 20 mils. Again, it doesn't have to be perfect because it doesn't matter how much water I use. What matters is how much chemical is actually there. I'm going to dissolve these and I'll be back. All right, so both of my compounds are now fully dissolved, and we're going to move on to the next step. The next step is we're going to mix them, okay? And when we mix these two solutions, this is when the chemistry is going to happen, all right? Right now, I have 2 colorless solutions. Might be hard to tell, obviously, in the video, but the powders that I originally had are fully dissolved, okay? And now when I mix them, and I'll show you, hopefully you can see it a little bit on the video, okay? It turned bright white. And that white color that you see is solid forming, all right? It kind of looks like it turned into milk, right? But this is a precipitate. It's like, it almost looks like hand lotion, okay? I mean, it's pretty thick, and again, it's the precipitation falling out of solution. So this is the chemistry we wanted to see. Now, the next step is we need to filter this. We want to capture or collect what was formed, the solid stuff. But I don't want all of that water or the other chemicals that are still left over in my solution. So I'm going to set up my filtering apparatus and show you guys that in just a little bit. Okay, so I've moved over to the other side of the room where I have my filtering apparatus set up. Step 5 in your procedure said that we should weigh a piece of filter paper. This little paper disc is filter paper, all right? So we are going to be pouring this precipitate and solution through the filter paper in this apparatus. I did take and record the mass of the filter paper right there. So my filter paper is 0.593 grams, all right? Again, we'd like to record that. If you were in the lab, we would absolutely need to record that as a part of this procedure. I'm then going to take my filter paper and I'm going to put it in what is called a Buchner funnel. This funnel on top is put on what's known as a Erlenmeyer flask. Okay, Erlenmeyer flasks are the triangle-looking ones like this, but this is more specifically a vacuum Erlenmeyer flask. So there's this side port over here, which I can hook up to a vacuum pump. So behind me on the cart, as this hopefully stops trying to tip over, There we go. So on the cart behind me, I have a vacuum pump. All right, and when I pour this onto my filter paper, which I'll begin doing in just a second, the vacuum pump needs to be turned on, and essentially it sucks all of the air out of here and creates pull or suction through the filter paper so that as I pour this, all of the liquid is getting pulled down and through, but the solid obviously can't go through the paper and it gets collected on the filter paper, which we're going to grab later, and then we're going to dry it in the oven on the back of the room that I have as well. So I'm going to do that. I'll turn it on, I'll start, and I'll show you a little bit, and then I'll pause it and finish it up so you don't have to watch me do this whole process. Actually, when you do this type of filtration, you do want to wet down the filter paper beforehand. And the idea there behind that is that now it's got a tight seal around the edges so that I'm not, essentially, when the water hits, it doesn't immediately run off to the side and I lose some of my precipitate in the process. If you wet it down like I've just done and you turn the vacuum pump on, it'll kind of create a nice seal so that we don't lose any of our sample. So I'm going to turn this on. I'll show you just a little bit of how this is going to work, and then I'll pause it and finish it up without you guys watching me. All right, so I've poured through as much as I can, but you'll notice, if you can see, I still have white stuff in the beaker, right? And I want to transfer all of that over. I don't want residual product that I'm trying to calculate and collect stuck in my beaker. So this is where we go back to using distilled water. This is a wash bottle with distilled water, and it doesn't matter how much I use. It just doesn't matter. So what I'm going to do now is I'm going to rinse the sides, and try to collect as much of this as I possibly can. Because this, if I don't collect it, is going to completely screw up my results. I don't want to leave, 30% of my sample stuck in this beaker. So I use the distilled water, I rinse, I pour it in, I rinse, I pour it in, and I try to transfer as completely as I possibly can. This is called a quantitative transfer, all right? We're transferring every last little bit of our sample. So I'm going to do that right now. Again, I'll come back in just a second. All right, so I'm done transferring over my product, my precipitation reaction that we just completed. You'll notice my beaker's still a little dirty. It's going to be really tough to get every last little bit. I've sprayed this down and rinsed it quite a few times, but this is about as good as I'm going to be able to get at the time, so it is what it is. Inside my funnel right now, I have the filter paper, and it's obviously still wet, but there's a whole bunch of white powder trapped in the middle now as I was pulling that and drawing that through. This is called a watch glass. All it is basically like a giant contact lens is what it kind of looks like. And it's just a holder for my filter paper because that filter paper is going to be very, very flimsy. So I took the mass of this as well. Okay, that's further down on the procedure. I'll show you that right there. So the mass of my watch glass is 49.968 grams. Again, we're going to need that to analyze the data in just a second. But I'm going to take my filter paper out without spilling any of my sample. Okay, and I'll kind of show it to you. If maybe you can see it. I don't know if it's kind of washed out. But there's white powder stuck on there now. And I'm going to place that on a watch glass like such. And now I'm going to go place this in the oven. So I'll turn my camera here. And way back there, underneath the clock on that cart, that big gray box, that's just a drying oven. It's really no different than the oven you have at home. But obviously it's for chemical drying and things like that. So I'm going to place this in the oven. We're going to let it dry. I'm going to take the mass, and then I'm going to place it in the oven again, let it dry again, take the mass, so on and so forth a couple times. And then we'll have our final results, and we can analyze the data that we've collected today. All right, so I have dried my watch glass with my sample multiple times. Again, it's going to be tough to see because it just seems like the light kind of doesn't quite let you see what you need to see. Maybe if I shade it. Or now you can kind of see the powder a little bit, maybe. But yeah, I have all my powder on there. I've done multiple drying cycles. And now I'm going to take this and mass it, all right? Previously, I had taken the mass of my paper. I had also taken the mass of my watch glass. So all I need to do is put this whole thing on there so that I don't lose any of my sample. Because again, it's a powder, right? If I breathe on this or sneeze on this, it's going to go flying everywhere. So it's nice to use the watch glass because it's nice and stable as opposed to just the piece of paper. So let me put this on the balance. I'll turn my camera and show you what I'm up to. Okay, so I have it on the balance. I have closed the door, and now I'm going to read the mass. And my final mass after I am done drying here is 52.063 grams. Okay, so I'll show you that number. There it is, 52.063 grams. That's the total mass of my watch glass plus filter paper plus precipitate that I've created. All right, so now what I'd like to do is, you see there's a bunch of questions on the back and on the bottom here. I'm going to go to the smartboard. We're going to go through them really quickly, and I'll more or less, work through these problems with you. I'll probably ask you to pause and let you try them, but we're going to analyze the results that we've just done. We'll do an error analysis on this and see how far off I was. Hopefully not too bad, but it's not the most perfect technique in the world. Yeah, and then we'll call it a Friday. All right, so let's run through the questions down below. I want to start with the definition. All right, so I have here net ionic equation. I think this came up last year, but it sure wasn't a whole lot. Let me explain what a net ionic equation is, because this is kind of a big deal in this class. A net ionic equation is a chemical reaction without spectator ions. Okay. Now, the word ion, all right, we know that means a charged particle, right? An atom with a charge. The word spectator means it's like, if you're a spectator at a football game or a baseball game, what are you doing as the spectator? You're watching. You're doing nothing, right? So a spectator ion in chemistry is an ion that is in your solution or is a part of the chemistry, so to speak, but it's not actually doing anything. All right, and this is kind of a big concept as we move forward this year. So here's the reaction on the back side of your lab sheet. I'm going to go grab my lab sheet. I'll be right back. On the front side of your lab sheet, you have this chemical reaction, okay, and you're more than welcome to balance that. It's a really easy balancing. And when you do that, you should get, let me just do it really quickly. 1, 1, 1, 2, right? I mean, super, super easy. So on the back, on my slide right here, I'm starting on the top of the back side, all right? So let's go through this. What I have done, and the difference between the reaction on the front and the reaction on the back, is I have dissociated those ions, all right? I had on the front side CaCl2 and Na2CO3. Those were the compounds that I had on the front for the reaction. But on the back here, I have broken them apart. I have dissociated them. And here is why, okay? When you dissolve salt compounds in water, and again, salts we'll talk about a bunch about later this year, but when you dissolve salts in water, they dissociate. When we took calcium chloride and we took sodium carbonate and I dissolved it, when those molecules dissolve, they no longer exist as CaCl2 molecules and Na2CO3 molecules, but rather they exist as ions broken apart in the water. Okay? So this is a much more accurate way of representing what was in those solutions prior to me mixing them. On the product side, I have the solid that we produced. The calcium carbonate, CaCO3, with a little S by it, that's the precipitate. That was the white powder that was created after I had mixed my two beakers together. But we still have two other things in our water, okay? We still had sodium ions that did not turn into a precipitate, and we had some chloride ions that didn't turn into a precipitate as well. Here's the deal. Last year, we would have given you this reaction like it was written on the front of this lab sheet. But this year, we're going to learn about dissociation, and we're going to learn that when salts are in water, they break apart. So it's more accurate to write it like this. But here's the next step. Look on the left side, the reactant side, and look on the right side, the product side. You'll notice that on the left side I have 2 chlorides, and on the right side I have 2 chlorides. On the left side I have 2 sodiums, and on the right side I have 2 sodium ions. They didn't change. They didn't do a darn thing. These are what are the spectator ions. We're going to cross them off. They're irrelevant. Nothing happened. They didn't do anything. They were there before. They were there after. They are unchanged. So they're not actually undergoing any part of this reaction. They're ignored. We're going to ignore them. We cross them off. And then we can rewrite this, okay? The true chemical reaction that we had occurring was we had calcium ions, aqueous. By the way, the little AQ stands for aqueous, which means something dissolved in water, plus carbonate ions, also aqueous. So these ions mixed with those ions, and that is what turned into our solid. That's our precipitate. That's the reaction we care about. So this is called a net ionic equation. It's showing only the pieces or the parts of this chemical reaction that actually changed, right? The sodium, the chloride, they were both there, but they didn't do anything. They're spectator ions. We cross them off. All right, number 2. Use the masses of sodium carbonate and calcium chloride to predict the mass of calcium carbonate that should form in your experiment. Hint, this is a limiting reactant problem. Spent a little bit on that, I'm sure, but let me give you those masses from earlier, all right? Way back in the beginning of this problem, I told you that I used 1.947 grams of sodium carbonate. I also told you that I used 1.961 grams of calcium chloride. These are your reactants. What I want to figure out is which one of these was limiting. In other words, which of these is going to run out first as a part of my chemical reaction. The way you solve this, and I'd like you to try without me, is solve for the total grams of product, which, remember from our balanced reaction in the previous slide, is calcium carbonate, okay? Do some factor label, all right? This is our balanced reaction. How many grams of product can each of these reactants possibly make? Try it. Please pause the video, do some factor label math, do it twice, and remember, whichever one of these produces less, that's your limiting reactant, okay? Give it a shot, come on back. All right, I sincerely hope you paused, but hang with me. So let's go and convert our sodium carbonate into grams of calcium carbonate, the product, all right? And I'm going to give myself a little extra space. I probably should have moved this downward, but that's all right. We'll just write it back again later. But now I'm going to convert from my moles of sodium carbonate to moles of product, which is CaCO3. And then last but not least, I'm going to go from my moles of CaCO3 to grams of CaCO3. And I'm going to get an answer for the product, okay? I'll then set up the next one. The next one I had 1.961 grams of calcium chloride. I'm going to go from grams of calcium chloride to moles of calcium chloride. And I'm going to go from moles of calcium chloride. Oops, that's not good. To moles of calcium carbonate, which is the product. And then last but not least, I'm going to convert that from moles of CaCO3 into grams of CaCO3 and solve that, okay? I'm going to pause it. I'm going to write all this stuff in and come on back, but that's the setup, right? That is the setup you need to solve both of these factor label problems and figure out this limiting reactant. So I'm going to pause it. I'll fill it in. I'll come back. All right. I have punched it all in. I've entered all of the numbers. I hope all of my molar masses are correct. I'm sure I'll hear about it if they're not, but this is what I got, okay? When I started with 1.947 grams of sodium carbonate, in theory, I should be able to make 1.839 grams of calcium carbonate, the product. I started with 1.961 grams of calcium chloride, my other reactant, and with that, in theory, I should be able to produce 1.769 grams of calcium carbonate. Which one of these can produce less? It's the calcium chloride. Okay? This, with what I had taken as a part of my setup, this is my limiting reactant. That's what's going to run out. So in theory, if everything went perfectly and I didn't screw anything up and everything was wonderful, in theory, when it's all said and done, I should have 1.769 grams of calcium carbonate produced. That was the white precipitate that I created. And again, I haven't done the numbers yet, but the theory is that that's what I should have gotten, right? I should have made that much stuff. So, which mass of the precipitate after the first or second drying better represents the amount of dry precipitate collected? I've already kind of asked you this on the first homework assignment, right? Why do we want to dry things more than once? It's to ensure that all of the water is gone, okay? That's really important. It's a good technique. So I did this more than once, all right? And it stabilized. The mass of my watch glass and the powder and the filter paper that I had, it was stable, so I considered it to be fully dry. All right, so how much precipitate did we collect? Let me find my sheet. Where the heck am I putting this stuff? All right, I have 52.063 grams. Okay, and that's the watch glass plus the filter paper plus my calcium carbonate. So I need to subtract the watch glass and I also need to subtract the filter paper. And when I'm done with that, this should give me my grams of precipitate that I actually had in my experiment. All right, so let's subtract this. And I'm getting 1.502, if I'm not mistaken, I hope. Okay. So that's how many grams I got from my experiment. All right. Now, theoretically, in theory, based off the math from the previous slide, I should have gotten 1. Oh, come on. Oh, well. Sorry, guys. 1.769. So I'm a little short. But I think that makes sense when we start considering the errors. All right. So now let's talk about errors in this lab. All right. Oops. Yeah. Okay. So we're going to do a calculation. All right. This is the standard normal percent error calculation. We're going to take the value that we recorded from the lab, known as the experimental value. We're going to subtract it from the accepted value. The accepted value is what we calculated, like factor label paper pencil from problem 2. Okay. This is the setup for percent error. So let's set this up with the numbers that we've just solved for. I have the absolute value of 1.50, what was it? 2 minus 1.769 divided by 1.769. I multiply this by 100, and I'll get a percent error, or how far I was off in my lab. So 1.502 minus 1.769 divided by 1.769, and then absolute value, so I'll make that a positive number. I'll just flip the sign here. And I'm getting 15.09% error. That's not great, okay? But it's not a perfect lab technique either. I wouldn't expect you to get great results from the way that I have done this lab. And there's a couple reasons why. There's places where I'm going to inherently have error in the process, right? So this is where I'd like to leave you. On the next question, the very last question of this lab assignment is list one potential error where a student ended up with more mass of calcium carbonate than they expected. Now, this is the exact opposite of what my data did, right? My data got less than I would have expected, okay? But think about the opposite. Why or how, in theory, could we have ended up with more mass of calcium carbonate than we would have theoretically expected? And then the next part of this is, what's an error where they ended up with less mass? That's what I did, right? My results gave me less mass. So what could have maybe been an error that would have given me that as well? Please write something down for each. I'll give you credit for this assignment. Turn it in. There is a spot to submit it on It's Learning. Again, much like the homework assignments that you've done, take a picture, okay, and upload it through It's Learning. I would greatly appreciate it. And if there's an issue, I'll shoot you an email. But I'm all done. I know that was a little longer than I expected, but that's okay. Have a lovely weekend, guys. Monday, homework topic 2 is due. We'll finish up 1.5. We'll jump into 1.6, and we'll just keep on trucking. Have a great weekend.